And they call it R. They call it R here and K here. Yeah. Let's call this K. If K is larger than N, right? 4 against 3. So equal is 1. That would be this diagonal. Yes. And I suppose I need this one as well. So if K equals 0, it's also 1. I want to reflect all these numbers. We do the reflection immediately, then I reflect this one onto that one. So then I only need this. What does reflection mean? That means that we just change K. K becomes N minus K. Yes, if K is larger than if 2K is larger than N. Let's do that here. Don't want to support N being negative. Yeah, I was supporting this. Okay, just don't support N being negative then. So like the table here, that would be up there, which is just all zeros. But it's kind of nonsensical. And then k being less than 0, yeah, there's also all zeros. Might as well include that, because I have to check that after this thing here. If k is larger or equal than n, then 2k is obviously also larger than n. So this can be removed now. But then k becomes a negative. Or not. K can be arbitrarily large now. Yeah. So if now k is less than or equal, and this is super close to this one because I just mirrored it, less than or equal 0, then if k equals 0, it's 1 and otherwise 0. So then we got all those zeros and also all the zeros on this side and all these ones and all these ones. And we know that k is less than or equal n divided by 2. So now I only have to support 1, 7, 21 and 35 and not the rest, which is not mirrored. Now note that the number of things that I need to remember then, cache, for n is 7 is 4. And for n is 8 is 5. 1, 2, 3, 4, 5. And for n is 9, it's also 5. 1, 2, 3, 4, 5. In other words, divide by 2 and add 1. We are now dealing with just following table. Hello, Colored Universe Tube. All other nicknames were used, I assume. Nah, the repeat of n is a bit silly. 3. I want to continue this till at least 7, I think. 4, 5, 6, 7, and then I changed my mind and went to 9. And then this row is 1. But we don't need to store the ones because we already returned those. So I'll erase them in a second. I suppose. So k is never going to be 0? Oops. No. it's not, because if k is equal to 0, then this is true. We already returned that one. Okay, this table, I have to copy it. 0, 1 on 1 is 1, 1. There's a 1 here. And then we get 2, which is this 1 plus 1 is 2. And then here we get 3, 4, 5, 6, 7, 8, 9. I don't need this one. So the 2 and the 3 are both divided by 2 is 1 plus 1 is 2. So we have a 1, 2 here and a 1, 3 here. And then this one needs one more, which is going to be the sum of 4. That is 6. Oh, that is just 2 times this one. So this is new, is 2 times that one. On this is 2 times that one. Yes, of course. And then we get here 10. And this is 15. 6 plus 15 is 21. 28. Plus 9 is 37. Could not remember it. Indeed, it's not true. 36. Yeah, well, it should have been even, of course. 8 plus 28 is 36. 28, 21, 15, 10. Yep. There were 2 of those, and then we get here 20. 2 times 10. 15 plus 20 is 35. 21 plus 35 is 5, 6. 28 plus that is 30 plus 40, 54. Yes. And then here we get, no, just look here, 28, what? What? No, 1, 8, 28, 70. And then here we get 1, 2, 6. Yes. And so on. And we do not need to remember the first column, so I can remove that as well. For example, if n is 1, then we can have a k of 0 and 1. If n is 1 and k is 0, then this is not true. But this is true. So we return 1. And if n is 1 and k is 1, then this is true. And then k is set to 1 minus 1 is 0 again. So then this is true. And then we return 1. Well, you're helping me by keeping me company. It's nice. Have a seat. But I'm doing things extremely slow, and also it's not involving much, just addition and multiplication so far. So if you can follow it, then it's then we have fun, right? So I'm trying to write a formula. Sorry, I'm trying to write a function that returns this table. So r here is k. So for example, n, if you pass n is 5 and k is 4, then 5 must be returned. And the way I do that now is by saying, yeah, but 2k is 8, is larger than 5, so let's change k to 5 minus 4 is 1. So now we return this one instead, and that is also 5, because, yeah, you see, that's just mirrored everything up. It runs up and it goes down again, and these numbers are the same as the numbers in the beginning, every column. But now I want to store that. We want to cache it in this vector here. So the way this is going to be stored, so after doing these two things, we have dealt with all the zeros on this side, on this side, which are not shown, and with all the ones, and with all the numbers on the right of this diagonal here. Amazing, isn't it? With just two compares. And also this one is unlikely, because you should never call it like that, but I'll support it anyway. Then that means that the rest of the code must be able to deal with this triangle here. And if it does, then we have finished our function. And I'm going to cache all values, so we have to store all these values in the vector. And obviously I'm going to store 2 first, and then 3, and then 4, and then 6, and then 5, and then 10, and so on. So where in the table do we have to look if we get an arbitrary n and an arbitrary k? For example, k is 2 and n is 8. Then I want to find the index into my vector that belongs to this 28, so I can look it up in the vector. Which means that I need to get, well, what is the index? This is stored at 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So how to convert k and n to 13 if k is 2 and n is 8? Well, that ends with plus k. So we're going to do int index is, we'll call it a cache index, is something plus k. Why plus k? Well, because if k becomes 1 larger, then we want to go to the next one. If k becomes 1 larger again, we want to go to the next one. Yep, so then what is the dot dot dot? The dot dot dot, that belongs to this n, because this is just going to be a function of n now, is the index before the index that we have for k is 1. So for example, I'm still looking at the, let's say, what was I looking at? 8 and 2, this one. And that index was 13, but now we added 2, so this must be 11, and then plus 2 is 13. How do we find the 11? Where's the 11? Well, the 11 is the last. The index belongs to the last entry in the column before that. So 7 should return 11. 6 should return, well, 3 less, so 8. 5 should return 5. 4 should return, is it 5? 0, 1, 2, 3, 4, 5. Yep. 4 should return, and so on. So we can put that even in the index here. That's what we'll call column for index. I do plus, so 3, sorry, 3 must return 0. If n equals 3, then k will be 1, because there's only the only one that is valid. We're going to add 1, and we need to index 1, so this must be 0, this part. So we could call this index minus k. And this one is the index of that one, which is 1. And this one must return the index of that one, which is 3. And this must return the index of that one, which is 5. And this must return the index of that one, which is plus 3, is 8. And this one must return the index of that one, which is plus 3, is 11. And n is 9, must return the index of that one, so that is 4 more, is 15. And so on. Now, what if n is 2? If n is 2, then we know that k is going to be 1, and we must end adding k, must end on index 0. So that means that it must be minus 1. And n is never 1, because we already dealt with it. Okay, so now how to get this column, this function of n. Well, let's just be lazy, I guess, and ask internet. I'm gonna fill in the last 10 anyway. 10. This was 9 plus 36. 120, 210, 252. I said it's some kind of quadratic, but with an integer round off in it. So I could probably figure it out on my own in 5 minutes, but let's just type it in on integer database. Not sure if the -1, it will be there. It should be, but let's skip the -1. Just going, 0, 1, 3, 5, 8, 11. And was it 15, 19? This does not include the -1. I'm going to try to add a -1 in front of it. Yeah, well, why not? The negative determinant of an NXN matrix. This +3, +3, +4, +4, +5, +5, +6, +6, +7. So it is the right thing. And the formula is x to the power 3. You're going to be kidding me. Oh, it's a generating function. Why is this so difficult? Oh yeah, that's what I was looking for. Thank you, Wesley Ivan Hurd. I'm writing a function that returns a binomial stored in a vector. Now the floor is automatic when we're dealing with integers, so that happens automatically after dividing by 4. So we're going to do n plus 2 times n minus 2, which is my quadratic, like I said, and then divided by 4, which is then rounded down. And now we add k. So there we are. Now check it. For example, our test case was, I think 8, 2. That should be 13. 8 plus 2 is 10. Times 6 is 60. Divided by 4. 60 divided by 4 is exactly 15. This is not working. Okay, now I'm confused. Yeah, 15 plus 2 is 17. 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4. What did I do wrong? Oh, we need an offset. Because this bloody thing starts with -1. Yeah. What I want is to start with -1. Okay, we can add a -1 in front of it. For n is 1, I want to get -1, but their thing starts with n is 0, I think. So nobody knows what this is. Offset 0,5. I think we just have to subtract 1 from n to like that. Keep the same formula but fill in 1 less. So now we had 8, that becomes then 7 plus 2, 9 times 7 minus 2 is 5. So 5 times 9 is 45, divided by 4 is 11, plus 2 is 13. Ta-da! It totally works. Okay, I'm convinced. Only one test suffices. Yes, it is. That is binomial, yeah. And choose k, exactly that. I'm just dealing here with the compression because I want to cache it in a vector, which is one-dimensional, and well, binomial has 2 coefficients. So my cache index is this, so I might simplify that a little bit. -1 plus 2 is plus 1. And this is on n minus 3. Which then obviously works, well, probably for every value, but and we even have n is 2. So if now we fill in n is 2 and k is 1, then we should get 0. That's the first index. N is 2, so that is 3 times -1. Uh-oh, that's -3 divided by 4. I'm not convinced that will give me -1. So maybe I do need a floor. The floor really goes to always to the negative side. That would give me -1. I think that the default round off is towards 0, right? So it's different than floor. Either that or special case n equals 2. I'm going to use the floor, I think. No, I can't, because they are integers. So before I divide by 4, is there not a better way to get I can add a constant here, then divide by 4, and then subtract the constant again. That would work, I guess. For example, yeah, we add 4 here, and then subtract by 4, divide by 4, which means that we added 1 too much, and now we subtract that 1 again. This should work. Because it must be faster, Adam. It must be fast. I mean, calculating 3 factorials is a lot of work. It must be so fast that I have no other choice than caching it. So this is still about caching. It's nothing to do with the binomial at all. Pure caching. Would work for any table here. Any table that has any numbers here in that are fit in that triangle. Let's just work out this polynomial. So we have n squared. This is n times n. And then we have minus 3n plus n. That's minus 2n. And minus 3 plus 4 is plus 1. So we can do n times n minus 2, because that's still positive. Plus 1 divided by 4 plus k minus 1. Check again. For n, so for k is 1, this drops out. And this should return now the index in this column, which starts at 0. For n is 2. Fill in n is 2, then we get 0 plus 1 divided by 4 is totally 0. And for n is 3, it should be 1, so fill in 3. That's 1 times 3 plus 1 is 4 divided by 4 is 1. And for 4, we should get 2. 4 times 2 is 8, plus 1 is 9, divided by 4 is 2. Now, one more, or shall you just stop? I believe it's correct. Then we can do the following. If AI, unlikely, cache index is less than binomial's size. Now do the likely. Likely is that we already cached it. Oh wait, that means that, yeah. So if you already cached it, then return binomial's cache index. Otherwise, we did not cache it, which means you have to assign it and then return it. Yeah, maybe I should then do the unlikely thing, assign it and just return it at the end. Now we have to calculate the binomials. Okay, a random place, we are somewhere, and any value that we have can be calculated by the subtracting 1 from n and then and subtracting 1 from k and not subtracting 1 from k, just adding those two. Yeah, sure, this is binomial n minus 1, comma k minus 1 plus the binomial of n minus 1, comma k. And now the function is finished. So let's do a test. I'm just going to print out that triangle there. For in the outer loop n is 0, n is less than 10, plus plus n. Inner loop int k, k less than 10, plus plus k. Yeah, try to make it fit nicely. That would be something with set width. But, I don't know. Is it working? So not working. Comparison. Obviously. Set width has not been declared. Well, then maybe it's set W or standard set width. It was standard set W, I think. No. Yeah, bit width. No, I don't think so. Top, 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 top. Yay. Okay, let's run the program. Core dump. It did not work. How disappointing. So this is already wrong. This should be the first entry. And it returns a 1. It should be a 2. Surprised. It is officially impossible to write a program without any bugs the first time. Just like bang, it works right away. Immediately. N is 3 and K is 1. Cache index is 1. Cache index is 1. Oh. Yeah, okay. My vector is empty, so that's not going to work. If this is larger than that, then we have to... Oh, that's a problematic. Yeah, I can't just resize the vector, because then we fill in a few zeros, resizing it, we resize it a lot. And then after that it thinks that it already exists. So maybe I should extend it to this plus a test if it is 0 or not. Which would mean that I never return 0, but then calculate it as well. And then that means that I should never have to calculate anything that involves a 0. I think that's correct though. Just do that. Yeah, it is it's like this. If the size is too small, or the thing was never calculated, we just had a resize. but I don't like that one at all. Yeah. No, 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 no. Cannot do this. If it is, if we get that, so I have to check it again. My God. Might as well do it in 2 steps then. So if cache index is larger than the size of the cache, resize it. And then if it was never calculated before, calculate it. Yay, now it works. So this should be the table. Oh, it doesn't look correctly. Or does it? I don't know anymore with my binomial here. It does not look correctly. It's not correctly. Where does it deviate? Oh, I have 2 2s here. What? What in the world? I think we started with n is 0. So at n is 0 we have a single 1. That's correct. And then we have 1 1, and then we have 1 1 1. Okay, that's wrong. Why is that wrong? This should have been a 2. It's already wrong then. So this must be correct, this row of 1s. And here we have indeed a repeat. The 2 2 looked weird, but it should have been 3 3. No, it's, yeah, 3 3. This. So it was calculated as 1 plus 1. If this one would have been correct, then this would have been a 3 and this 2. And then this would have been a 4. And then I think everything else would have been correct. Because, yeah, it just looks correct. It seems that only that one goes wrong. It's K1 and N is 0, 1, 2. N is 2, K is 1. Should be returning a 2. Is 2 times K larger than N? No. Is K less than or equals 0? No. K is 1. Cache index is, well, this should be 0. Is this greater or equal to size? Yes, because vector is empty. Oh. Ha ha. Ha 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 ha. Yeah, I'm putting a 1 in there already. That's the reason. I put 1 where the 2 was, and then I thought it was already cached, so yeah, then I just went with that. So this is the correct thing then. And yes, that looks correct. My editor is NeoVim. Do I recognize this? 126? I think so, yeah. 84, 126 twice, yeah. Very good. Good, good, good. The binomial works. Now I can pre-fill it with, I pre-filled the factorial also, all the way up till where it's a bit larger than integers. And this thing is not growing that fast. I guess I could just print it out. So for int cache binomials, standard cout b, comma, and that is my cache then. Cannot convert. Oh, sorry, that's a big number. So here we have the contents of the cache. And we can theoretically do that till a few thousand or something. So we don't have to calculate it every time. But it seems fast enough. Point being, n is not going to be that large. That's the whole idea, I have to admit. We're talking about if I do 100, and it's already 10,000 big. It's very, very, very big. No, wait a minute. We did this doable, I think, because I should stop as soon as it is larger than fits in an integer. So that's pretty quick. These numbers are just way too large. What are you now telling me? Oh wait, this is just it's not the cache. This is the cache with the commas. So we could put in the vector until the first number that is larger than fits into an int, which is which number? Still fits. Let's say up till 2 billion. That's 1 billion. So it's difficult to see like this. This is too large. 2, 3, 1, 2, 3. 28. Let's just start with copying it till it is definitely too large and then figure it out later-ish. So, I'm afraid I don't have extended regular expressions, so let's do 1,000,000 with 6 digits. This is billion digits, or what is it? A billion digit. 9. So that would be up till let's try 2 or 3. Yeah, this is probably too big, so we cut it off from there. Fuck. Well, maybe I should put it in the triangle shape. Nah, just fancy. Too fancy. Great. One vector with a bunch of binomials. No, let's keep it. Right, check. N squared is 100. What is 10 here? 100 minus 20 is 80 plus 1 is 81 divided by 4 is the same as 80 divided by 4 is 20. Yay. Seems to work. Now, what else can we do? Now we have the binomial. We should be able to calculate Bernoulli numbers. Bernoulli numbers. Already have tableized a bunch of them, but let's allow us to make arbitrary ones. How to do this? I think I want to implement B2. Well, this should be possible to just put it into a single cache. Let's write a new function. The polycomma starts here. So I want a function called b plus, because I want to return plus a half for b1, int n then because you can start with these as well. Also unlikely. And then return B2. So I want to have a cache for all the B2. And the index is obviously just going to be n divided by 2. See, n is 0. You also get here for n is 0. So just index, the cache index here is simply n divided by 2. And then we do if again unlikely, we did not calculate it yet, aka cache index is larger than or equal to the Bernoulli. All the Bernoulli numbers. No, it's too ugly. Numbers. Size. Calculate them. And yeah. Otherwise, just we have it, so we can just return it from the cache. So that looks a lot like the previous function, I would say. Or not. I have to do the resize trick as well, maybe. Oh, I have no idea, Paul. I'm just doing my thing here. I'm not walking and talking Google or YouTube search engine, for that matter. Oops. Yeah, I have again this same problem. Now, if everything is cached, I think we're going to call this with increasing n. So then by the time, increasing with 1 at a time, so then by the time that n is larger than, or n divided by 2 is larger than the size of the vector, we have all the previous values. Could I guess theoretically just assert that this is the case for now? In other words, if it is larger, then it should be equal to the current size. Do we have to cast that again, even for an equals? Probably. Well, at least for incremental values of n divided by 2. If that's not the case, then well, then I have to do the same thing as for the binomial. Just resize and then also check if it is still 0 or not. And since this is the case, we can just do a pushback. So now we do that push back, and then the value that belongs to this n. So now finally we can do some math. What is the nth Bernoulli number? Well, with n even. Calculated. I think that, call this, it's a polygamma still. Well, maybe this is the best way then, because we're going to calculate all the Bernoulli numbers cursively. So to have the next one is equal to the sum of all the previous ones times a binomial divided by that, all subtracted from 1. So we're going to use this formula, I guess. Probably not much you can do about having to do the full sum. It's at least better than a formula like this. Recursiveness is way better in this case because I intend to calculate all of them. Or I should do the zeta function first. Then we can do the b to n at once. But not really liking the looks of that. I mean, you're supposed to get a rational number. And this already has a 2 pi to the power 2n, but okay, it's probably just falling away against the same factor of pi here from the zeta function. So this looks like, no, it's not. This is just that slow function. I mean, this is really like 3 loops inside each other. And while the recursive function had, no, I have to find it back. This one, it's just a single loop. I'm going to go with this one. Now I have to move that to my editor. Doesn't want to do that. Well, how about now? Yeah. B plus is implied. B M equals 1 minus the sum of k is 0 till m minus 1 of the binomial for m comma k times bk divided by m minus k plus 1. Did I do that correctly? 1 minus the sum of k is 0 to m minus 1 of binomial of m over k times the bk, the over of divided by m minus k plus 1. I think that's correct. And binomial is returning a CPP int, right? It's not a rational. Yep, it's just an integer. So if we would calculate this as a CPP int, then we can start with that. I keep forgetting how that is called. It's a denumerator. I think I have it already mentioned somewhere. Gotta be kidding me. I do. Denominator, that's it. Denominator. Okay, I'm going to call the denominator m minus k plus 1. And of course you have a CPP end, that is then the numerator. Yep. The numerator is then well, the binomial for m comma k. And then one term of the sum is yeah, and m is just n, so just 2 places within, I guess. So we start with 1 and then we subtract every term. So next b minus becomes the next term. For k runs from 0 to n minus 1. And where it is binomial over n minus k plus 1 times one of the previous Bernoulli numbers. Now we can push that back. I think this works. So if let's say n is 0, then we come here. Cache index doesn't exist. Next b is 1. k is 0 and must be less than 0, so we skip the whole loop. And we push back 1, so b0 equals 1. And if I look at this one, that will do b2 0, which is the first elements of those two. And that is 1 divided by 1, so that is 1, which is correct. And then the next one is 1/6, because this is b2's, yeah. The half is already taken care of. If n is 1 is a half, to do that here as well. N3 is 0, sorry, yeah, N3 is 0, and N4 is then the 1/6. I think this has a good change. I'm just going to print it for, let's say, first 10 Bernoulli numbers. That's in. Bernoulli numbers was not declared. Better declared then. No, that looks good. The 1 plus half, 1/6 minus 1/30, and so on. Yeah, let's print a few more. Because it looks already so good that it's probably just working like a charm. Let's print them up all the way up till and including 20. I'm good, but I'm not so good that I recognize this number. I think I recognize the rest. Let's find a list of Bernoulli numbers. We have them here actually. So a 6, 1/30, 142, 566. 691, 2730, 76, 36, 17 divided by 510, 43867 divided by that, and that is, yep, indeed, actually correct. Well, could hardly be wrong at this point. Now see how fast it is. What happens if I try to print all the Bernoulli numbers up till 1000? Crazy, I think. Pretty crazy, yeah. But if it's fast, then hey, then we don't have to worry about it. That's fast, yep. Awesome. Oh my god. And still divided by 6. It's a recurring thing. Yeah, also divided by 6. This one is divided by something much larger. Yeah. Every now and then it's just 6, 5, 10. Yeah, there's another way big number. That cannot be a coincidence, right? That those denominators, they're really small. They just stay small. 42. Wow. And another 6. Suppose the reason is that this number is just way, way, way bigger, and therefore it's likely to have a lot of prime numbers in it. And this one is small, so it only has small prime numbers. So it's likely that all those prime numbers in the denominator just cancel out against prime numbers in the top one, simply because of the size difference. But that last 2 and 3 never cancel out. So 30 is divisible by 6. Are all these numbers divisible by 6? That's a good question, I think. From the looks of it, that is divisible by 6. This is 3, 9, 4, 12, 5. Yep, that's also divisible by 6. So I guess that divided by 6 is something that we could just take out, actually. Just 1/6. It's just always there. 6 times 7, right? Well, pretty cool. Now we have arbitrary numbers or Bernoulli numbers. What is next? I think I don't even want to keep the other one. Do I want to fill this with the first whatever, the first 50? Yeah. Let's fill it with whatever fits again as int. Just not that much, but why not? This is too big. This is too big. That fits. This one fits. So we can go all the way up till here, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But it's to n. And oh, that is what I'm caching. What is the first one that we stored? Well, 0, yeah. Just these. And I've got what I was counting to the image. That was too big, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. Okay. Because I look silly if I don't do that. So let's just think about though. It's this one divided by that one. No. Let's type them all over or what? That's just 1. So this becomes 1/6. So 1 divided. No, I just have to insert them all. How do we alternate that? Substitute every comma with I think I need something more fancy than that. Substitute all integers plus not working, of course. No, just do it the stupid way. All integers followed by comma with CPP rational comma something comma You don't have a backslash 1 or it just doesn't fill it in? That's better. No, whatever. 1, 6, 30, 42, 30, 66, 27, 36, 5, 10, 7, 9, 8, 33, 30, 1, 3, 8. Yeah. Now I have to wonder if this... Let me first try this compiles. No. Yeah, it'll look good. Might as well go even further, I guess. Yeah, like 100 at least. 100. Hmm? Hmm. Forgetting the minus signs again. Just do a minus star. Yay. That works as well then. Okay, looks much better. Then I'm going to remove the previous ones. Hello, 20MTR. I should turn on the lights because I can't see my keyboard. I'm not so sure anymore that I need Polygamma 1. I think I need Polygamma 0. The rest is just nah, you know. And this is not compiling anymore because I just removed B, or B2 rather. Yeah, put it here. If 0. So I want to add, I want to find out how we best can calculate Polygamma 0. I'm going to turn on the lights. Okay. I'm pretty sure that is going to involve the Bernoulli numbers, of course. Like, in the end, we are going to implement Polygamma 0 in terms of the Bernoulli numbers, right? But coding includes basic. What to do? Well, I have to admit that it would be nice to just find it. Yeah, it's an awful lot of time. I feel that I'm nearly dead. Well, I'm 59. But I'm getting there, you know. I remember that a very, very large part of my life, I kept thinking about the year 2000, because Nostradamus had made a prediction for the year 2000. A very large part of my life. I just kept thinking, year 2000, oh, that's so far away, so far away. Am I still alive in the year 2000? And then many, many, many years later, I was thinking again about the year 2000. That was the prediction of Nostradamus. I have to, you know, I will be alive. Yeah, I'm going to check that. But it's so far away, you know. Oh my God, I cannot imagine the time that it will turn 2000. And now I'm living in 2023. 23 years past the date that I've been thinking about as something laying far, far in the future. That old I am. It's really horrible. But again, my brain is not as degraded as that of my parents yet, who are still living. Bernoulli my ass. I'm gonna find Polygamma. The Polygamma function. So the Polygamma M, poly comes from the fact that it's just a whole set of functions depending on M, is the nth derivative of, well, just phi of z. And m0 is therefore just this, the phi z. Thus, phi is, and this is the one that I need, I think, is actually just gamma prime of z over gamma z. So maybe I should make a function of this too, and then I can do the division and then we'll have it, right? With the gamma function is an, what is the word? That's how it starts. Extension, yeah. Gamma z is an extension of the factorial into the complex numbers. Well, plus or minus 1. It's like gamma plus 1 is the factorial or something like that. Or the other way around. And prime, yeah, I suppose that's a derivative of the gamma function relative to z. But we're not dealing with complex numbers, so maybe, you know, there's a better way to calculate this than doing it for every complex number. Phi z is a digamma function, so my polygamma 0 is actually called a digamma function. Which is a derivative in itself. It is a derivative in itself. Well, Yeah, I think this is what I wanted to see, and I suspected that already. To a very large z, it is just a logarithm of z minus 1 over 2z. Well, guess what? That is simply the integral of what we found for the gamma 1 function. I mean, the gamma 0 function of this whatever Digamma function here is the derivative of my polygamma 1. So we integrate this one, then you get the function that we need. And this one has an 1 over n as its first term. So I mean, I'm making a Taylor series here in 1 over n. So I think we're already almost done. I just need to do a logarithm, a natural logarithm of the first argument, and then the integral of the gamma 1 function polygamma 1 function that I already had. Although I still have to do the integral, but that would be well, just m is 0, I guess. You see the factorial thing, but also the plus 1. For the factorial, it would have been z plus 1 times that. But I just have a z here instead of a z plus 1 in front of it. Let's just scroll down till you see the Bernoulli number pop up. Hopefully it does. No, maybe not. Hmm. Da 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 da. We found it. Yep, this is the one that we want. Apparently, we can calculate this Digamma function by subtracting 1 from the argument and then take the natural logarithm of that, and 1 over, well, half times 1 over that thing, and then subtract a sum of Bernoulli numbers divided by something. Not anytime soon, Demir, no. I think I'm, I don't know. It's too difficult for one person, let's put it that way. Okay, I'm going to need the difference between two polygamma functions, which then comes down to the difference of two logarithms, which is the logarithm of the ratio of those two things. This probably should just calculate it as is. And these are, well, all rational numbers. I can just keep them rational numbers, I suppose. Then we have an infinite position. Though I have to cut off that sum at some point. Yeah, I definitely need to be able to calculate an ln of something, where this something is an integer. I wonder if we can already see that this goes to infinity. Because even if this would drop out, just the ln goes to infinity, of course, if you let z go to infinity. And what I'm going to do is add the difference between, let me think, I think the ln of some prime number divided by the next prime number. but then the sum of that till infinity. So something a little bit less, that would be negative. What? I don't know. Well, it included code here. Oh, it didn't. Should have clicked on that before, I guess. It mixed the two up. This is the high position one. Yeah. I'm using CPP end here. The Dreamy Warlord. Are you telling me that you are subscribed but you never get a notification? It would be totally YouTube if they don't send notifications to my subscribers. Yeah, well, if you don't have to subscribe, trust me, but it's what it is for, to get a notification. So if you check every day and you miss it, the streams all the time, then maybe you might want to check that out. Yeah, well, okay. I was just worried that YouTube might shadow ban me somewhere. You know, I used to have way more viewers, but on the other hand, I don't think my videos are that interesting. So it's probably all me that I have less viewers left. Maybe those people were there because I was working on Vulkan. Stopped working on Vulkan. No. Not sure. Anyway, the Digamma function. So I had a web page here about it. This is it. So we want to have the log. Let's subtract 1 first. Okay. In. Nah, let's do it like that. HPPP float Z is static cost. HPPP float n minus 1. Da, 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 da. So my n is now z plus 1. And then minus 1, and then we get z. Yes. And then we have to calculate the ln, the log of z, minus 1 divided by, whatever, 1 divided by 2 times z. Let's return that. Nah, let's say that is my result. And then we return that. And then we're going to print it for large n. Well, 1,000,000. No, I can't do 1,000,000. 1,000. Out. No, it's not debug. Well, maybe it is, but out. The Digamma 1000. Yes, absolutely awesome. Make. Hey, Snow. So how about a cup of hot chocolate with that? Or are you out of it? Oh, I'm not plotting anything. What is wrong here? I didn't add the incantation for the big precision. Make. Okay, we have a number here, and the question is, how close is that to the correct answer? Well, we'll have to ask Wolfram Alpha, which is not having any top. I just close stuff here. Let's be bold and start closing a few things. So what is this? Quadratic forms. Prime sieve using binary quadratic. Oh, I still want to look at that. Yeah, this is a paper by Atkins. That is just interesting. That we finished with. What is this? Dwarf. Oh, fuck yeah. I have to do something with that too. Okay, let's stop closing. I have to rewrite my ellipse WD because it's not supporting Dwarf version 5. I support 3 and 4 now, not 2 and not 5, and they keep upping the version. So I finally gave in a while ago and then started rewriting it so it works with lib dwarf or whatever, lib DW I think, and then it stopped halfway. So I'm going to fix that on stream at some point. It's a plan, but now we're still doing math, which because it's just way more fun. What was I going to look for? Oh yeah, Wolfram Alpha. Too bright. Too bright. What is this? I want to calculate I'm gonna call it Digamma because, well, who knows? Maybe also Wolfram Alpha understands what I mean. Of 1000. The answer is this. Which is what I have calculated as well. Well, at least up till the 1, 2, 3 digits. But because it is 1000th, we just know that, of course, we have to add 1/nth. A half-nth, or did I already do that? I don't know. We must be getting closer by... I thought I typed in that number. Typed in the... I didn't. I didn't. Totally no ln. Maybe ln. Nope. You've got to be kidding me, right? I just close some tabs and immediately I need them again. I thought I already typed that over. No, probably didn't. Now you have to look it up again. Oh, there it is. Phi. Can you give me the UTF-8 for a phi? EA, the Digamma function. Oh, that's not what I wanted. A psi or something like that. Psi, yeah. Oh, it's psi. Well, thank you, I can copy it. The psi of, I would say it's a gamma actually, or it's a capital gamma. I mean, it's called a digamma. Why would they not use a gamma? Well, gamma looks different. Those math guys are so confusing. 1 plus z is the ln of z plus 1, oops, 1 over 2z minus, it's not going the right way, strange man, the sum of j equals 1 to infinity of b to j are divided by 2jz to the power 2j. Why is this even working for complex numbers apparently? Let's check it. b2j minus yes, it's good. It is good. Now we are here, and z is then, well, n minus 1. That's correct as well. And then we take the log of z and we subtract 2. Yep, and yeah, subtract. Plus big change upcoming. I'll bet now we're a lot closer to this value than before. Yes. 0.960725. Now this is, oops, all of this is correct. Much better. And now it is larger than what it should be. So now I was thinking, well, what, because now we're going to subtract stuff. So it better be larger instead of smaller than it was smaller. Very good, very good. Okay, now we're going to subtract stuff. And well, this. Let's use, well, that's just 2j here, 2j there, 2j everywhere. Why am I even running over j? Oh, wait. That's because I want to run over all the even numbers. Okay. Yeah. For int j2 equals 2 forever j2 plus 2. So my j2 stands for 2j. So we begin at 2, of course. 2j is 2, and then every time we add 1 because it's all double. And then we want to result minus, because this minus, every term, which is the Bernoulli numbers, the B plus, that's a B plus, okay. B plus returns a rational number, while this is yeah, just an int. I'm inclined to do the whole sum as a rational infinite precision. And then at the end, cast it to so let's say we do that, and then we go to rest. But we'll do that at the end then. To begin with the rational. Let's call it S. So n is a CPP int, and z here was, I'm going to need z, I am going to need z. As could be a CPP int as well. Somewhere at the bottom. So we have z is n minus 1, yeah, and then the rational, we start with the rational as 1 divided by 2 times z, that would be that one. And then we're going to subtract from s all these terms. So this is s. And then in the end we're going to return the log of static cast to that of z. Otherwise you're not allowed to take the log of it. Plus an s, but I think also that requires a static cast. So the b plus of j2 divided by 2j times z to the power 2j, which then also is well, not also is an no, this is a boost, Dreaming Warlord. Boost multi-position. What's it called? Multi-position, yeah. These. So I'm having this namespace here included. That's why everything looks like non-boost. God, this is from boost now. And this is, and this is, and this is. Loads from boost multi-position. And these as well. Or guess that it is an int, so let's try to start like that. That would be to the power 0. And then the first time we enter this loop, j2 is 2, so I need the square. So we can multiply this with the square of z. And then the next time around, j2 is 4, so we calculate, multiply it again with the square. So then this becomes z to the power 4. I think this is correctly done. The only question I have is if it is allowed to divide a CPP rational by a CPP int, but maybe it is. Shouldn't it be? To J, that's not going to work now. Therefore we have to write J2. Uh-oh, it's slow. No. Oh, I never stopped it. Oops, yeah, stupid. Infinite loop. You have to stop this at the moment that things are precise enough. Oh, it's pretty difficult. If there are floating points, I mean, this is a rational business. If there were floating points, then I could just compare it with some epsilon. But if I do that now, then I have to cast it to a floating point every time, every loop. Just to compare it with this epsilon that I have here. Hmm. It is, I don't know what to do. Can we construct it like that? I guess the answer is no. No met jouw function voor een call to rational adapter blah 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 blah. Okay. Just can't do it. So instead I'm going to do delta is divided by, because that works. Does it? Doesn't it? Just checking. And then if delta is small enough, then break out of the loop. Yeah, now what is small enough? And how do we compare that? Well, I think I can do the following. We do epsilon inverse here. I'm not using epsilon anywhere else, right? Just deleted that code. Yeah. Well, commented it out. So inverse would be the minus sign. Remove the minus sign. Not sure if the power is gonna work then. Probably power returns int to the power digit. Yeah, I don't know what it returns. But it's an integer. So let's try to put that into a CVP int. Let's try to convince this thing to return a CVP int. See if this compiles. Fact. Let's print epsilon inverse to see that it is a reasonable thing. Yeah, of course, it's not working. Well, that looks like 10 to the power a lot, so that's good. So delta is going to be less than that if I want to get a denominator and the numerator separately from delta as CP int. Go back to CP int. No, pretty cool. So if the denominator is like a gazillion times larger than the numerator, then delta is so small that we stop. It's lying. A rational adapter. That's because of that, I suppose. Oh. Oh. Sometimes I feel like it's doing it on purpose, just to waste my time. I'm lazy, I guess. Okay, documentation is my resort after ChatGPT has wasted an hour of my time, and then I look at the documentation. Now, how precise is this one? Uh, 8812. I might as well highlight it because it's just going to be exact. No. Oh, it's not. It's not. Oh. All of this are already wrong? Why? How? Impossible. Possible. Shocking, man. Only those are correct, and then it's failing 0006 against 3998, and yeah, that's not the same thing. What is wrong? Did we stop too soon? We just break out way too soon, maybe? Yeah, stopped at 4. Okay, that makes sense. So it breaks out way too soon because it's negative. Brilliant, brilliant. Could not have thought of it. I'm gonna guess that it's always a numerator that has a sign, so let's do the absolute value of that. Hmm. 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 Oh yeah. Boing. 100% correct. Well, all the way up till here, and we can't check it any further. But I'm guessing that it is just correct all the way up till the end. But how to be sure? Because the annoying Wolfram is not wanting to give me more digits, I bet. I want more digits. No, I'm not going to do it. Well, there is a way. You can think about it like this. It's probably till the end, but certainly till halfway, right? So if I just double the number of digits, that one is equal all the way up till this point, then this one was good till the end. So I'm just going to double the number of digits. It's very easy. Digits. Make that 400. And highlight everything. And it's not equal. Okay, let's highlight all of that. That is equal. And then we have some stuff here which is still equal. Still equal. That's not equal. Also not equal. So too short. 13, 3, yeah, okay, so it's good till there. This is good. This is wrong. The last part is not good. Why is it not printing stopped at? Did I delete it? Deleted that. This is using 226. Wow. So that's using the Bernoulli number of 226 already. Wow. Way more than I had before. And delta should be at least, yeah, here's the division. So it is pretty small, the delta. Yes, I think I have to cast delta to HP float before printing it. Yeah, that's weird. Yeah, it's seriously weird. So this is off. Well, delta is here, which indeed is like way smaller. So the delta is tweaking the digits here that it shouldn't even be printing. Why is it printing there? Yeah, so why? What is wrong here? What is wrong here? It starts off with we need the logarithm as part of it, and that's a larger part of it. I mean, now it's accurate till, I don't know, 80 digits, and then it starts going wrong. So it has to be something. So I'm starting with checking the logarithm. So we're just going to return the logarithm. Just the logarithm, and then see if that is correct till yeah, well, the number of digits that I print, which is the maximum digits for the current float that I'm using. That should be just, you know, correct till the end, right? Slightly confused here. It's not even a little bit the same. Well, a little bit, but literally up till there or something. Nope, not even that. So the 1000th is off again. Okay, never mind. I think I've got that term. Or did I? Oh, yeah, sorry. Digamma 1000 returns a logarithm of 999. So I'm comparing it with the wrong number. That's definitely not being equal then. Thousand is a bit much anyway. I'm using Arch Linux. Yeah, that's better. That is much better. No, that is indeed the issue. The problem is in the log. You see, this is what it should be: 293592, etc. 6. There's a bloody 6 here, and that's about the point where it goes wrong. So the reason that it did not give me the correct value is that the logarithm is not correct to that position. Aha, very bad of this boost implementation. Now let's see if we can calculate a log then with a hard precision and then cut it back. I don't know how much harder that I need though, but so if I'm trying 1000 digits, then I guess it's going to still not be equal, but then at least we'll see if there's more or less a constant or not. What is that? Oh, I'm only printing 400 digits. 500. Oh. What? What? It's off. It's off already. Whoa, exactly the last digit that is printed. Oh, I did round it off. Oh, I did round it off. That's just the last digit here. So the 3/8 is rounded off to 4 because of the precision. Yeah, I'm not using the right thing here, or am I? Because I am in. I'm trying to print it like that. Huh? It's definitely not printing 1,000. Why is it not printing 1,000 digits here? I'm having a 500 here, but well, that's for... That was done before. Maybe... No, not a bug. Now it goes on correctly. 603. 2 till 3 5 also correct. It's all, everything is correct. There's the full 1,000 digits. Some reason it's printing way more than 1,000 digits now. Strange. Very strange. Unreliable logarithm. And if I'm not mistaken, this is just way more than 1,000. 1,027. I'm not asking for that. Oh, the reason is that, yeah, okay. You get more than you ask for. The precision is at the moment 1,027. I would guess that it's rounding it off to a multiple of 64 maybe, or about that. 1,024 divided by 64 is a little bit than 16 times 64. 1,024. Let's ask for a multiple of 64 precision. Say 256. Oh. Seems to be correct all the way till there. Now we have 11.7 and here 23.18. Okay, well, we have a dot here. Maybe it's also counting a new line. So remove the dot on the new line. Now we have 257, and the last digit might be equal by coincidence. So, okay, 256 is the precision. It just prints way more than that for some reason. That is highly annoying. So I want to set the precision just 2 digits. Still printing more than that. Something is horribly wrong with this precision thing. It's as if you can only set the position once and then it just sticks to that. Maybe it is because I use fixed here. Anyway, now I'm using digits twice. Let's put it here as well then. Good. No, that looks a lot better. Conclusion, at least now, it is accurate all the way up till the end. Maybe it just went way beyond the number of digits that I specified. So we can also test this one if it ends on the correct number. So let's copy this. I just have it still. Just try 1024 digits. And then see if this is all. No, it's not. Well, the last digit could be wrong, so I should have done up till there. Yes. But that is a rounded off wrong, so it's not a round off. It's just the last digit is wrong. Not too bad. That not too bad. Yeah, okay. I'm convinced that my Digamma function is all the way up till this number of digits correct. I'll use 256. Deleting this, sorry. Then we can do the following. We can you can write a function that returns, yeah, just simply, I think, the summation between two things. So when S and T are small, or rather when the difference between them is small, we can calculate that exactly using, well, just this formula. So let's start with that. So we do just a rational. Let's do an int. Start with 1 over S, which assumes that T is not less than S. And then we add one divided by u, where u runs from S plus 1 to all the way till T equal to. Yeah, and then that's gonna be huge quickly. I mean, but it is exact. And then, well, we have to cast it because we want to print something that we can understand. The cast is more for human understanding than anything else. Otherwise, we just have two absolutely incomprehensible integers that are divided by each other. And we can print it out for some values for S and T. Let's say 1000 to 1100. Well, how do I check this? This would be the difference between two Digamma calls, I think. I should have done something that I can check. Yeah, let's do 1 divided by 3, 1 divided by 4, plus 1 divided by 5. How about that one? I can do that from my head. 0.45, right? Yes, that worked. And then if we do till 6, then of course it's going to add 1/6 to that. So we're going to get, we're going to get 1/6 something. 1/6, yeah, that looks good. Yeah, that is correct. So the function is correct. Now how to, I'll have to make it large again. Now to do this with the Digamma function. I'm going to guess something, you know, like maybe it's a Digamma 1100 minus the Digamma of 1000. Maybe it is, maybe it isn't. No, not that bad. 0.09. We have the first 2 digits behind. Well, it's in the order. It's almost in the same order. Yes. And the difference between these two is probably just, you know, well, we're off by 1, I think. Cannot be anything else. Let's start with trying adding 1 there. Hit in 1. Boom, 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 boom. So that's how we do it. That's almost 256 digits. Well, not quite. To the actual valid number of digits, but we start with a 9, so I might as well add that new line. I think this is 255 digits position. Okay, I'll leave it that. No, pretty impressive. Now, the sum. I need my prime numbers then. Prime numbers. How do I do that? VI series had the primes in it. pool, capacity, primes, generator. Yep, that's my primes. And I'm going to run over why only 50? Give me all the threads you can have. All the threads. Okay, and then we're going to have a sum stored as an high precision float type. This is my series. And that is starting with 1 plus a half. And then we're going to... now let's do all of them. So we have a prime type, I don't know, forever. Prime type PS generator next prime. Which gives me the prime numbers. Let's check that. No, let's make that finishing loop. I guess those are prime numbers, 2, 3, 5, 7, yep. So we're going to get 2 of those, called prime 1 and 2. And then we're going to have an n that starts at 1. And then my series is actually a sum, so you just start at 0. And then we're going to do series plus equals the partial harmonic sum of the current value of n till n plus p1 minus 1. So the first prime is 2 and n is 1, so n plus 2 minus 1 is 1 plus 2 minus 1 is 2. So now we're going to add 1 over 1 plus 1 over 2. Yep, the first two of these. So that's 1.5. And then we are going to subtract from that. Well, let's just update n first. And then we're going to do the exact same thing, but for NP, for P2, and then subtract that. And then update n again. And now we print series so far. So this should start with, I can't calculate it from my head, but I have a calculator. So 1 plus a half, so okay, 1 divided by 2, minus, so 1 divided by 3, minus 1 divided by 4, minus 1 divided by 5, 0.716666, and that should be the first thing that is printed. So I'll put a break here, and then we can test that. Yep, 0.716666 forever. Except that I forgot again to set the width. Perfect. Now, I think this is my my question. What is this going to? And if we do not do the break here, well, we're just going to get the next two prime numbers and then add partial harmonic sum for n to n plus p1. Subtract that, and so on and so on and so on till forever. And the question was, does this converge or not? And if it converges, then what does it go to? So let's just let it run, you know, see what happens. Now, as you can see, it's at 1.147. And it's slowing down in calculations like crazy. It started to go fast, but now it's going slower and slower and slower. Plus, we seem not to need this precision because it's random all the way from here. So let's do 10 digits. Now I have 64 digits because, you know, apparently that's what we work with. I'll use, I don't know, 16 digits then, because we really don't need that much in the beginning. But the precision that we are calculating with has nothing to do with that it slows down. It just slows down, obviously, because, well, we are adding stuff in a loop with the size equal to the prime numbers, and every line is 2 prime numbers further. So the further we go, the larger the prime numbers, the longer the loops, the slower the next line is being printed. And it's just going slower and slower and slower. But it grows. Now you might think that this is, you know, already stabilized at 1.148. In other words, it will converge to something, but no, it's not converging. This is going to infinity. I'm pretty sure that it's going to infinity. Can you imagine how slow, how many lifetimes of the universe we'll need for this computer to even show 2, let alone 100 or a Googleplex. I think I'll let it run at some point till, I don't know. It's definitely going to reach 1.15. If we let it run enough, we can wait for the 1.15, I think. But it's getting seriously slow now, right? Okay, now let's print the value of n at the same time. So we print here n, and then we print that number. Dude, super big. From about n equals 1,000 or more, we can use the other formula. But hey, why not wait till 10,000? Because this was so fast, it's unbelievable. So we'll do this until about 10,000, and then we switch to using the polygamma, or maybe I should do until n divided by p2 equals something larger than 1,000. So instead of printing n, I'm going to print n divided by the largest prime number. Yeah, as well as n, because we still need to know till which n we want to run. Okay, that's a lot further. If you want this to be 1,000, then we have to seriously wait a long time. Not going to do that. Not going to do that. Yeah. Let then wait till it is 100. Okay, so how long does this take? I think we can wait for that. Nah, even n is, sorry, it's just nonsense. I don't think p matters a lot. Well, it matters a little bit though. I'm not so sure. Okay, I'm gonna go with this one. I don't know why, but it was fast enough. Let's do int n outside. So and then we do while n is less than that number. And then we do forever. Yeah, the same thing. Except that we use not this, but this. So that would be the Digamma of 1 plus the second argument, which is n plus p1. Minus the Digamma of the first argument, which is n. And then here you get the same thing, but then with p2. Overflow. What happened? This is not fitting anymore. Wait a minute. N, yeah. Who is using an N here? Let's use a CPP int, so that won't happen again. The Digamma accepts a CPP int, right? Yep. Doodle-doo-doo. Now what? Cannot convert CPP int to uint64 type. Oh, the partial harmonic thingy. Yeah, well, okay. I'll make this an int then. Yeah. It's probably still going to infinity. It's just slowing down. And it's still going insanely slow to infinity, I must say. Yeah, well, if I parallelize it, then it would be 30 times faster. It's just hardly going to help much, right? Even if I got it 30 times faster. You know, the problem is the logarithm, right? There is a logarithm in it. And it's a logarithm of, well, because you subtract stuff. So it's a logarithm of z, which is n-ish. So this n here. But then minus a logarithm of this of n that's a little bit larger. So that it's a logarithm of one of these numbers divided by the next number, which is very little bit larger than 1. So this is a positive number. And then till infinity. And that's still infinity. Period. It's just going to infinity, but so incredibly slow. So incredibly slow. That we'll never, ever, ever be able to witness it. So if you want this 1 billion years, then maybe it reaches 1.16. And then the end of the universe, we are at 2 maybe? Yeah, something like that. Oh boy. Okay, I'm having a reasonable feeling now for how fast it is, or how slow I should say. So, ding, 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 here, once a second or so. And that's at 1, 2, 3, 4, 5, 6, 7, 8, and the 9th digit after the floating point. Sleep well, dreaming warlord. Have nice dreams about, well, not about warlords, because that's you yourself. I'm going to see if it is equally fast if I increase the number of digits. Two, 64. If you're here, you have the feeling, oh, this is going to converge to 1.15. Oh, no, it isn't, because it passed it. I know a way to speed it up. Compile optimization. And of course only printed every 100th time or so. Every 64th time. And C. That's in series. I did do that. Oh, that was the last one. Yeah, that is indeed not possible. What this is, what was it anyway? I think a CVP int. CVP int should work. Maybe just, yeah, of course this works as well. 2 strings. No, is it faster? I don't think so. Oh, it prints only every 64th line out, so it is faster. Definitely faster. Kikomi, no. I'm not paid for it, so I'm just playing, having fun. Yeah. Is this going to be the constant of Carlo Wood? Or is it just going to infinity? One or the other. I guess I could just let it run for a month, and then it's gonna be so slow that I might as well call it a constant. Nobody will know. They'll never know. What's the expression? Nobody will know. Yeah. Well, no, they will never know. That's the expression. the impressive part is that this is not slowing down because of the Digamma stuff implementation. It just keeps printing these lines at full speed. And we'll keep doing that forever. Now let's see if we can find a constant like this. A constant that begins with 1.15, yeah, 006. Could be. What's conversion calculator? No, I don't see a constant pop up, but okay. We have not enough digits, I guess. I could write more digits, just assuming that it is. The 2 is already changed. Okay. Could try one more. 4 maybe. Too many physics just random numbers that people measured or something. No, this could be it. Eventually it goes to this, which is the sum of the all cubes. Nah, not. It cannot be that because it's. I have prime numbers involved. It should be something more random than that. Well, this one. 2 over the square root of 3. The largest real root of... yeah, and that's listed here. Of course. My constant is not in here, then it's a new constant, that's for sure. Though I probably don't have a constant. That's an annoying thing. No, could add it to this list if we had something. Well, my personal feeling it has to do with pi squared, which is not even listed. Why would pi squared not be in this list? I'm going to do the following thing. Calculate it. Pi squared is that divided by 1.15. Nah, that's 8.58. That's a bit far off. From something nice. Okay, then not. Could be the logarithm of something. How about e to the power e to the e to the power. No, I can't find e. Still not enough light. Not enough light. You see my calculator. Thought it was below this one. Yes. E to the power 1.15006. Yeah. What was it? Oh. Maybe. Let's calculate the natural log of pi. Yes. No, it's too small. 1.14. Okay. Fun. But that were all the prime numbers up till 1 billion. Yeah. I can run can let it run, I guess, during the night. For all prime numbers up till 100 billion. That would be 100 times longer. I think that should pass the night. And then I think it's the end. I have to find a new project. I did ask on our mathematics on Reddit if this series is converging. See if I can find that back. Indeed. I ask it as me, yeah. Plus recommend. Nothing. Did nobody answer me? How do I find my last question and then my stuff? Profile, grid, avatar, document, explore. No. I just want to know. I just want to know the last post that I made, if any. It's weird that I show up as Carlo Wood here, because on my phone I don't. So what the hell is going on? I think I asked something on this forum. Yeah. Oh, that's my question. Does this series converge? Do you have comments? Here's the first 5,000 partial sums of this series. Cute. Considering I went to a billion or something. If it does converge, the value should approximately 1.15. Yeah. Well, thank you, but see if there's a conclusion here. I'm just trying to calculate it. Prime number theorem is equivalent to pk is about k log of k. What is that? Okay, times the log of k. And this implies p1 till pn is about n squared over 2 log n, but I don't want to justify it here. Using that estimate, we have p1 blah blah blah, blah till pn minus 1 is plus 1 is about n minus 1 squared over 2 log n minus 1, which is about n squared over 2 log n. So the upper and lower bounds on an are asymptotic too. Thus, an is about 2 over n, since each an tends to 0. The convergence of 0 is equivalent to the convergence of the alternating series a1, da, da, da. So you might ask, if an is about 2 over n, does the alternating series converge? I think this is too general a question to have the same answer in all cases, but I haven't given this much thought. What about using the usual alternating series test, since an tends to 0, an minus 1, log, Nobody gave a real answer, unfortunately. This one came close-ish. He did some attempt, but no actual So this question here must have been answered already. think this does converge. Do. If this converges to something close to 1.15, then we have our answer. It converges. Yes, it converges. Some of this here is the log 2, which is approximately 0.69. Not even close to 1.15. Actually, that is. maybe. Well, actually, no, that would be 1 every time. That's not true. Yeah, that would also be way larger. I don't know. Yep, and I closed that window, thinking I was done with it. Top, I mean. Just going to open all the close stops. Yeah, that's the one that I wanted. Sandbox, this can be closed. I'll close this one. And then that one. This I still need. $100 billion. Okay. Victor, don't ask me that. I don't know. I just figured everything out myself in the past. These days you have internet. look it up. You only learn something. Did you use the word learn? Yeah, you said learn. That means hard work and a lot of time. Repeating. Write a program. Write programs that implement it. Like what I'm doing now. Unless you spend a considerable amount of time on something, then you just don't really know it. Does help if you have a very good memory, so you don't forget anything, even though you spend just a little time on it. And then you can just remember a lot of things, and then by the time that you need it, and you will remember it, and then you think, oh, I had just something to do with this or that, and then you can look into it then. But even then, you still have to put in a lot of time at that point before you can say that you really understand it. Okay, can work with it. But is ChatGPT not lying to me, as usual? One minus a half plus a third minus, so it's summed, it is the log 2. Okay, it's not lying. Hello, Aditya. Sorry, Aditya. How do I get my 1.15? It's kind of strange, I have to admit. Why would it be all that much? This is... Looking here. This is 1 minus... Oh, 1 minus a half. Yeah, okay. So that doesn't say much, right? How did he get to that conclusion again? Okay. Value is not very important. And the offset is also not important. AN is equal to the sum of, well, is there a formula for the sum of all primes up till a certain point? This is n, and that is prime. I know the prime number, so I'm not sure that it printed it at the right moment. Can we work back from this to the actual value of n? Oh, this is n. This is just the sum of all those prime numbers. Damn it. So we sum the first two primes Right, thus round down of 508 47 535 prime divided by 2, I think. So that is the number of prime pairs that we have. Divided by 64. That would be a C of this. Rounded down. So I'm guessing C is that. 397,246. So that was 397,246. Is it divisible by 64? No, it's not. Why not? Just if I divided the thing by 64. Let's do 6207 maybe. Times 64. Let's just guess something, you know. That if it doesn't work out, then it wasn't that 8. That's divisible by 64. And that would be the 397,248 times 2 prime. Doesn't make any sense whatsoever. I don't think I can calculate. There are this many primes. Oh, divided by 2. Yeah, I'll start over again. I have 847,534. Divided by 2. So that's the number of prime pairs. I'm going to round down immediately. That's 25423 divided by 64 is that, so 397 times 64, and I get to completely different number, namely 25,408. Try that again. This is divisible by 64, as it should be. And it means that we reached this number times 2 primes. No, no. Why? Completely lost here. Maybe it's just too dark to see what's on my calculator. That must be it. Oh, I have a calculator here, but it's not as good. Maybe it's good enough here. Damn it. 508 47 535 divided by 2 equals, no, Want to make that an integer, like minus 0.5. And then that's the count, no, yeah, divided by 2, so that should be C, but I want to find the last C that was divisible by 64. Thus, divided by 64, oh, mod, yeah. Divided by 64 is that, yeah, it must be that times 64. I don't know what I called there. This is 397,246. 397,246. So that number is divisible by 64. Yes. And then multiplied by 2 is again that weird number. I must be cruelly stupid. 2, 5, 4, 2, 3, 7, 4, 4 times 2. I think I just divided by 64 and then multiplied by 2. So times 64 is, no wait, not times 64, times 2. 2.42, 3744. Okay, so again, this is divisible by 64, but I no, but 2542 3744 divided by 64 equals, okay, and I should have multiplied by 2, so now I multiplied by 128. Right, and now we have a number that is less than this. And obviously, if we add 64 to this, then the whole thing times 2 becomes 128 larger. 2 plus 128 is 7616. Yes. Good. And the last prime pair P1, P2 was okay. Now how do you calculate that? If C is this, then this times 2 is a P2, I think. For example, if C was 1, then this is 2 and 3. So times 2 gives me 2. That means that is P2. Yep. this on my calculator faster, I think. 2 times 2, 5, 4, 2, 3, 7, 4, 4. I can verify that. That's 2C, right? Yeah. Two, 3, 7, 4, 4. Times 2. That does not fit on my calculator. Okay, we have the digamma here of that number, which is my n. And he's talking about the n of this. Or like way less. I'll use keep using z, I guess. Nah. Yeah, just do one term here. So that is 1b b2. Oh, what is b2? not 1/6. I think that's the 1/6 number. Definitely starting as that, yeah. B2. Cache index 1. It's 1/6. Something is not right. Why am I subtracting the digamma of something that is smaller? It is smaller. If you do it like this, it is smaller. Digamma is, yeah, okay, larger mine is smaller. So subtract the smaller one, okay? Oh yeah, right. I was confused with this minus here. Never mind. It's talking about AN. Digamma of that minus the digamma of that is the ln of that plus. Well, that then becomes a minus, I think. No. Okay, let's just do 1 over 2 times the first z minus 1 divided by 2 times the second z. This term is already neglectable. So that's the difference. Sorry, I multiplied this one with that and vice versa, and then subtract them. Which one's larger? 2792113. That one's larger. So it becomes a negative. And the difference between the two is that one, a number, divided by no, I'm not mistaken. That one times that one, which is more or less a square. Hmm. No, it was negative. Did I not do that? I copied everything from there. Yeah, and then it becomes negative. That is, would be that one. So you have to compare it to this one. It's the same number. Minus 6413, 10 to the power 21. 6441, I mean. Yeah. I want to be 100% sure that this one is even much less. So that is 1/6 of let's fill it in. Times minus 1/6 divided by 2 times that 1 squared. How do you write neglectable? I have no clue. Negligible. I wrote it correctly, but it probably was this. Oops. Right. Yeah, just this, right? Which was that ln here. Which was that? 2c. Yeah, is that correct? 1 divided by 508 47 488 is that. Okay, and not. He said it was about 2 divided by n. And not 2 divided by that. Which happens to be... yep. .93. Zero 8. Yeah, it starts to become bedtime, doesn't it? Got a lot of those websites where you spend an hour or two editing a post like this, and then in the meantime you secretly timed out because, well, it doesn't show you, but you did, and then you click on submit, and then it says something went wrong, and you bumped all the way away. You lost everything you typed. It's just gone. Those are the worst websites. Oh well, I can live with this reply, I guess. This is, yeah, I don't know. Since this is wrong, in my opinion, the rest doesn't matter what he says. Yeah. This just makes me laugh. I mean, it's like a 5-year-old comes to you and say, "Look what I did," and then you pat them on the head and say, "Good boy, very nicely done." Or do you think he went, these are the first 5,000 primes? Well, it's still 1,000 times, no, 10,000, a factor of 10,000 less than what I did. Even if they are primes. I guess they are. I think I'm going to bed. Yeah, good to plan, Post Bunny. Let me just run my program for the whole night. Because what else can the computer do the only night? This is all the way up to 1 billion. 1, 2, 3. What do I have here? 1, 2, 3. 1, 2, 3. Oh my god, it's just 100 million. There goes my post. Oh, fuck me. Gotta be kidding me, right? Oh, that's really bad. That's really bad. No, I don't have time to fix it, so I'll just add a comment. Ridiculous. Let's do 1,000 times more. No, that's 100 times is enough, I think. So till 10, 1, 2, 3, 10 billion. Now I have 10 billion. And it was still printing a little bit too fast, I think. Well, let's slow that down with a factor of, I don't know, 4 at least. 5, 2. I'm using a power of 2 so that it doesn't have to calculate a modulo. That's just a bitwise end. Calculating the primes. The primes have been calculated. Why would I do so difficult, actually? I can... I can print the approximation of the summations immediately in terms of n. A equals, so print an and then 1 over 2 divided by n as well. And see if it compares. Let's do that. To the n is just 1 over c. Is this correct? So you said an is about 2 divided by n. 2 divided by n is printed as being, well, n equals 2 times c, because we have one here, an an, and an an here, so it runs up twice as fast as that. Yes, and then 2 divided by 2c is 1 divided by c, and that's what I print. Whereas the an is that n, where an was calculated as that one, for example, the very first time we enter. This is a, well, 0, and this is a1, or this is a1 maybe, and this is a2. Does it really matter? No. And then c is incremented, so n is 2. Yeah. So we start at a1. Of course, we have to divide by n. We start at 1. Correct. Print it. It's not correct. How could I say that it was correct? Conversion from... Oh, the Digamma is in high precision float. Of course it is. Well, this guy is correct. The guy is correct. More or less correct. Pretty close-ish. But does it diverge or not? Or does it converge? Still not very clear. Old top. Now I'm thinking about using threading as well, I have to admit. I guess I could just calculate, just in order get 60 primes in advance. The next 60 primes, and then just calculate everything in parallel. Who knows, I might be able to do it for all the primes up till a trillion. That would be cool. Yeah, I must say, it's pretty much stabilizing here. It is stabilizing. I'm suddenly convinced that that 5 is never changing. Probably the 6 is not even changing. It would be really nice to have, like, say, all the way up till here, and then maybe I can find out what kind of constant it is. Yeah, if each partial sum is roughly 2 over n, then it's converging, because um, the alternating harmonic series is converging as well. Well, that is converging to the logarithm of 2 for some mysterious reason, and this is way bigger. So maybe it is a logarithm of 2-ish, but then with a constant. Now, if it's a logarithm, it's a constant plus a logarithm, then it's of course the logarithm of the e to the power of that constant. plus a logarithm, which means that it's a logarithm of 2 plus e to the power something. In other words, it's just a logarithm. So I think the first thing I should do is e to the power of this, and then have a look at it. But yeah. .158 something. That doesn't look like a nice 2. Okay, but that could be 2 plus something. So minus 2. And that is then 1.50. Aha. No, it can't be. Actually, this would be... Yeah. Nah, nah. Not accurate enough. You know, it's bothering me that this is even. Why is this even? I thought it was the sum of all primes. No, it's not. No, it's not. What is it? We have a look at the program. It's N2. That is the sum of all bloody primes. N is 1. Oh. Okay. So, what? Is that a bug? No, we start with 1. Yeah, oh, I'm getting it. Yeah, yeah. It is, yeah. We start with 1 divided by 1 and then plus 1 divided by 2. And that is the first prime, namely 2. And then we subtract the next 3 and then add 5, subtract 7, add 11, subtract 13, add 17, and so on. But that means that n is 3 at the start of the next prime here, right? So it's 1 plus that 2. And then, so I was thinking it is the sum of all primes. And then, yeah, 2 plus an odd number is an odd number. And then the next loop isn't plus odd is again an odd number. So I thought it must be odd. But it's even because it started as 1, which is correct. It's 1 plus the sum of all primes up till that point. Now this number here is, in case anyone wonders, that's the n, the sum of all primes up till that point, divided by the last prime. So not really that interesting, I guess. And this, of course, the convergent variable that we're looking for, or constant, I hope. And this was a test which now I regret that I just didn't print this value divided by the other value, or just basically print n times a. That would be cool. That would be more or less 2. And it would be interesting to see if that goes to, I don't know, some constant. Some constant or not. I think I can do that much faster in a different program. Just keep calculating that. I would have to generate all prime numbers, and then this n here is basically then which prime number it is. So now we are at the 11 millionth prime number. And n is the sum of all primes up till that point. So I could do that in a very short time, a few seconds even, I think. seconds for a trillion? No, I don't think so. But certainly for where we are now. So we can do that afterwards, I guess. Once this finishes. Well, it never finishes, but after this I did run it for a few hours. I think I'm going to bed, let it run. Also getting the feeling that this is already stable. Might just be stable. Maybe not the 6, but I don't know. Keeps being dubious. This 6 is stable, I think. If I wake up and the digits are counting up like here, then we have something. Well, it's not going to happen. I think they are just the changes here are what you say linear width or whatever. The inverse of the current prime number, or well, something like that. So it's, I don't know, going before we are here, we need so much more prime numbers. It's ridiculous. Maybe it will be like here, changing. It's just, yeah. I think if I wake up, I might have certainty about the 4 or maybe the 6, but yeah, that's top. Oh boy, I feel like stopping it because there is an improvement to make. Okay, first of all I will do this. I'm just going to print n times a times an. I wish I could change this number of position digits here. It's just not working for some reason. Yep, a definite improvement would be to print both of them. Into before. Into before. a series before. And then I mean before this point, before subtracting that. So series before is series. No, that's just, it's not even worth printing actually, this. What? Just was printed. So minus P2. This is not worth printing. Stop printing that. Because what it converges to should lay between these numbers. So then we just know what is accurate already. Much, 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 much better. And that is fun. So let's do this one. Okay. Last thing, something like that. Yeah, that's much better, isn't it? So now we are already certain that these zeros are correct. Because the number that we're looking at is just in the middle of these two. So the 6 is correct. Yeah, way better. Way better. Now I can actually see what it converges to. With certainty. Not only that, also that it does converge. Well, I did leave it running for a long time, and then we had at the bottom 646, I think. And you can already see if you add these two and divide it by 2, then that's already for 646. So that's probably then indeed where it will go to again. So if we let it run again as long as I did before, then we have 646 here and 646 here. And then, oh, it's changing somewhere here. Just have to do it all again. But now we're going to get this much, I think. At least, yes. Which is a lot of digits. Especially when I can add them both and divide by 2 to get 2 more digits. And then if it is something that is not a completely new constant, then it should be possible to guess what it is, I think. No? With 10 digits or so behind the comma. But yeah, the prime numbers are involved, so maybe it is a complete new constant. Which was the whole reason, of course, that I was doing this. Making something, creating a mathematical constant that didn't exist before. And then I'll attach my name to it. Evil laughter. No, I printed it in the chat, yeah, 64623. So now I wish I already added them the divided by 2 and printed it as well. No, yeah. Can't have everything. Okay, I'm going to bed.